And you're on.
Hey everyone, welcome back to Virtual MOSI. My name's Jose, and this is the final day of our physics week. It's also Field Trip Friday. So we are going to go ahead and take you on a small virtual field trip of some of our great exhibits here in the museum that deal with physics. And we're actually going to start right here. Behind me we have our world famous bed of nails. Now the bed of nails is a really awesome exhibit, and all you really have to do is lie down on the flat surface here, and then you simply press and hold this button. Now you might hear a noise. That noise is actually a motor that's raising all of these nails, which you see right here. And if you could look up, you'll notice I am actually lying right here on a bed of nails. Now you probably have some questions, and if you do have questions throughout the video, I encourage you to go ahead and type them up in the comments. We're going to go ahead and read those comments and get back to you guys, giving you those answers as they come up. But notice, these are actually real nails, and one of the first questions that a lot of people tend to ask is, how come you don't get hurt? Or does it hurt? Like, what's going on? And the answer is, it doesn't actually hurt. And I'm going to let go of the button here, so you're going to hear that noise again. There we go. Now that the nails are down, I can sit back up. It doesn't actually hurt. And the reason for that is because of physics. So if you look right here on our bed of nails, we actually are explaining why it is you don't get hurt. And it has everything to do with this formula you see right up here. This formula states that pressure is equal to force divided over the area. That means that since we have so many nails and you're lying down or you're laying down on all these nails, there's less pressure per square inch, or rather per nail, because your weight is dispersed, it's spread out. If you were to try and stand on these nails, then all of your weight would be concentrated on a smaller area. And since this number here is smaller, that pressure would be bigger, and unfortunately that means that the nails could hurt you. So we definitely don't recommend that you stand or even try to do a handstand on our bed of nails, but if you lie down, it is perfectly safe. Another good way to think about this is to imagine that it's summertime, you're at the pool or in the water somewhere. You can't really stand on water, you just kind of fall right through. But if you lie down, you lie back and spread out, now you're spreading out all of your weight over a larger area. And yes, there is some buoyancy that you have to account for, but essentially you're able to kind of float on the surface of the water. So it's a very similar concept to this whole force divided by area equaling pressure. So once again, that is our bed of nails. It's one of our very awesome exhibits here at MOSI. But now let's direct your attention to this really cool thing here. This is actually our magnetic pendulum. Now, if you've been following our videos, then yesterday you saw Ms. Catherine doing some really cool pendulum art. This is much the same way. A lot of times, I've seen some of our guests take these little magnets and just throw it at the pendulum. That's not exactly the best way to get them to stick. You see, there's a trick, and for those of you watching this, here's a technique. You want to gently swing the magnet on the rope so that it swings back and forth like a pendulum, and eventually, once it gets close enough, it's going to go ahead and stick to the big pipe in the center. Now, if you work as a team, you can gently tug on this giant weight, which by the way, weighs about 300 pounds. And if you're doing very gentle tugs, you'll notice I'm actually able to move this. And as soon as you get that nice rhythm going, that giant pipe is going to swing in a pendulum-like motion. So it's going to swing back and forth, much like the pendulum art that you guys saw yesterday. And again, it's just taken a tiny push. So that's pretty cool, and this is a lot more fun when you have more people working on it, because then you can try and swing this in a circle and all sorts of different patterns. So that's pretty neat. This is our magnetic pendulum, and it's actually one of my favorite things to play with here in the museum, just because it's so large and awesome. But now let's go ahead and switch gears a little bit. We're going to go past the puzzles area for just a brief moment, and we're going to take a look at this giant contraption that you see behind me. This big contraption is actually what we call 1,000 to 1. And on this side, it just looks like a large table, okay? And if I try to move this, there's not really going places. There's a lot of force that I would have to do to move this big table. And if we look up and we follow what it's attached to, we suddenly realize that there are 3 sets of very, very large gears. And those large gears are actually mated to very small gears on the bottom. So if you look really closely, I'm going to try and do as I say, not as I do. We're going to go ahead and observe here. We have this large gear that's kind of meshing with this smaller gear. That is a very large gear reduction here. So we have a 10 to 1 gear ratio, followed by another 10 to 1 gear ratio, and then a final 10 to 1 gear ratio. If you're doing the math, that's 10 times 10 times 10. That's 1,000 to 1 gear ratios. But what does that mean? What is a gear ratio? Well, that means that if you wanted to turn this large table 1 time, you actually would need to turn the smaller wheel, which is attached to, 1,000 times. So if I move this, I have to move it very, very fast so that I can get some rotation. And if you keep an eye on the large table here, you'll find it is actually moving. It might not move very quickly, but it certainly does move. Now, what is the advantage of having all of these gears here? Well, if we're going from a little gear to a bigger gear, it allows us to kind of move with a little bit more torque behind it. That's why I'm able to turn this table just by using one hand, but I can't physically move this table by myself because it's much too hard. Now, if we somehow managed to do this backwards and we went from a large gear to a small gear and we turned that, we would actually get a lot of speed. And you might have encountered this if you have a mountain bike or a road bike at home. If you're trying to go uphill, which I know is kind of rare for Florida, but you typically want to go into a lower gear. So it's going to be very similar to moving the small gear here to turn the big wheel. And if you're trying to go kind of into overdrive, then you would make sure that you're pushing a bigger gear as you're pedaling so that when it ties to the smaller gear, it can go much faster. Kind of similar to the way that gears on a car also work. So that's pretty cool. And again, this is 1,000 to 1. If you're trying to do this backwards, you're going to have a hard time unless you've got several friends joining you to make this small wheel spin very rapidly. So this is gears, and there are gears everywhere. Anywhere from watches to bicycles, like I mentioned, and even car engines. So gears are very, very prominent. But now let's talk about another simple machine. This one is called a lever. And this is a special lever. This is actually a lever we like to call tug of war. Now, tug of war is pretty awesome. As you can see, it's a large piece of wood, and this piece of wood has ropes on either side. And those ropes allow us to place a person on each end, and then we can partake on a small challenge. So I've got my friend Michael over there. Hello. He says hello. And I'm over here, and we're going to go ahead and engage in a tug of war. So the goal here will be for us to pull on the lever and get it to our side. So Michael, are you ready?
I'm ready.
All right, then in 3, 2, 1, let's pull. Huh. Now, I saw Michael, he was putting his whole weight into it. I was able to do that one-handed. Now, that doesn't mean that I'm 3 times stronger than Michael or something like that. Let's analyze this real quick. Let's take a look and break this down. So let's do that one more time. Okay. All right, so 3, 2, 1, go ahead. He's pulling on it. I'm holding him with just one hand. And if you look closely and you follow the rope, you'll notice that the rope on this side is actually tied way up here. It's about 6 feet off the floor, whereas the rope on the opposite side, so I'll hold this up here, this is the rope on my side, the rope on the opposite side is actually tied only about 2 feet off the floor. So what does that mean? Well, that means that this side, where the rope is lower and closer to what we call the fulcrum, which I'll explain in just a second, this side, you have to do more work to get it to move the same distance. Whereas on the other side, more leverage. So it's considerably easier for someone on this side to tug on the rope and have that lever move that same distance. So it is technically cheating. So we're going to switch sides here, and you're going to see that Michael and I are not disproportionately strong against one another. So now I'm on the harder side, so let's see how this goes. Are you ready?
I'm ready.
All right, 3, 2, 1, pull. As you can see, it is considerably harder on this side and much easier on that side. And again, it's all about leverage. Now, where might you have seen levers before? Well, you could have seen them on like teeter-totters or seesaws. There's also, very common, on scissors. Now, let's look at the scissors real quick. These are very big for demonstration purposes. You'll notice that the very center right here is also what we call the fulcrum. And the fulcrum is just like this big center pipe that was on our lever. But what is the fulcrum? Well, that's the point around which the lever actually turns. And if we imagine that this is our tug of war, then the rope that is tied up higher has more leverage, and it takes less work to move that lever over distance. Whereas if it were tied on the bottom, it actually takes more work. So there's less leverage. The farther away you are from the fulcrum, the easier it's going to be to apply that force. But you do kind of have to move it a little bit farther. So that's kind of cool, and that is our tug of war. So right now we've talked about our bed of nails, we've talked about our magnetic pendulum, we even talked about 1,000 to 1 and our tug of war. It turns out there's many more cool exhibits like these at MOSI. So definitely be sure to check it out once everything goes back to normal. And actually, as an incentive, we are doing a special promotion. During the month of May, you get 30% off your memberships, which is cool because that also gives you a discount when you sign up for our summer camp programs. So that's definitely pretty neat. I hope you guys have enjoyed our physics week and our awesome exhibits here at the museum. I hope to see you guys here soon once everything is all doing well.
We do have one question.
Oh, we have a question. Excellent.
About 1,000 to 1, Brian would like to know what would happen if you had help moving the big one.
Ooh.
Would the little one spin?
So that is an excellent question, Brian. The question was, what would happen if you had help moving the big one? Would the little one spin? Let's give it a shot and see if we can get this to work. My theory is that, yes, it should work. Let's give it a shot. Which way do you want to go? This way?
Yeah.
All right, so let's give it a shot. Notice, it's going. It's just taking a lot of work, but we are getting it to move. Now, obviously, doing it this way takes a lot more work, but as you can see, we can get a lot of speed out of the little gear back there. If we hadn't all stopped pushing it someday. So yeah, if you move the big table with some help, or if you're the Hulk, then you can actually get the little wheel to spin And you can make the little wheel spin a whole lot faster than if you were to manually move it a turn at a time. So that was an excellent question. Thank you for asking. Do we have any other questions?
We do not.
All right. Well, thank you so much for joining us today. I hope you've had an awesome physics week. And as always, stay safe and keep discovering.